Hello, my name is QianxunMa. Today, I'm excited to present my analysis of the abalone age prediction dataset as part of the practical machine learning assignment. The goal of this project is to build a regression model that predicts the age of abalones based on their physical measurements such as length, weight, and shell characteristics. This is important in marine biology and fisheries, where age estimation helps with species conservation and sustainable fishing practices. Why is this so important? Fisheries worldwide use age prediction models to estimate population dynamics and harvest quotas. For example, in Australia, abalone fisheries set legal size limits to prevent overfishing. If abalones are harvested too early, their populations cannot replenish, leading to economic losses and ecosystem imbalance. With an accurate machine learning model, we can predict age without cutting open the shell, making it a non-invasive method to regulate fisheries. In this presentation, I will walk through EDA and pre-processing, feature engineering and scaling, model selection and training, model evaluation and performance comparison, bias variance trade-off, validation strategies and feature importance, and real-world implications and deployment considerations. Let's dive in. First, let's come to the exploratory data analysis and pre-processing. This dataset was retrieved from the UCI machine learning repository and contains 4,177 samples with 8 features and 1 target variable, rings, which represents the abalone's age. Before training models, we need to ensure data quality, checking for missing values and duplicates. One of the first steps in any machine learning pipeline is to check for missing values and duplicate entries. The good news is this dataset contains no missing values and no duplicate records. Next, using the AutoVis, we analyze the distribution of numerical features and identical key patterns. As we can see, length and diameter showed a strong positive correlation, indicating proportional growth. Shell weight and hull weight were right-skewed, suggesting that most abalones are small, with a few significantly larger outliers. And height had extreme outliers, likely due to measurement errors or biological anomalies. Next, let's come to feature engineering and scaling, encoding categorical features. The dataset contains a categorical feature sex with 3 values, male, female, and infant. We use label encoding to convert this into numerical values. We also handle the skewness in the target variable rings. The target variable had a skewness of 1.114, indicating a right-skewed distribution. This suggests that most abalones are younger, with fewer old ones. And we will also remove the outliers using Turkey's rule. Since extreme values in height and shell weight could affect model training, we applied Turkey's rule to detect and remove outliers. Next is the model selection and training, train test split and scaling. To ensure generalization, we split the data into 80% training and 20% testing and applied min-max scaling to normalize feature distributions. So here's the question, why do we use min-max scaler? Since features have different range, for example, length varies between 0.0, 0.14 and 0.81, while hull weight ranges from 0.014 to 2.82. We use min-max scaler to normalize them. Min-max scaler scales values between 0 and 1, preventing large values from dominating smaller ones. And then we train the following models, including multilinear regression, lasso regression, support vector regression, and so on. And we may use a cross-validation for model stability. Instead of relying on a single train set split, we use k-fold cross-validation to ensure model stability. Lastly, we will come to model evaluation and performance comparison. Models were evaluated using mean squared error, mean absolute error, and R-squared score. According to the R-squared score, multiple linear regression performed the best, with the R-square of 0.53, and the lasso had the lowest accuracy. Speaking of the bias-variance trade-off and feature importance, multiple linear regression is simple, interpretable, but underfits. Lasso regression has strong regularization, shrinks coefficients to zero. The decision tree overfits but easy to interpret. Random forest is the best balance of accuracy and variance, and SVR needed hyperparameter tuning for better performance. In conclusion, the best model is multiple linear regression according to the R-square with the highest accuracy. The shell weight and whisker weight are the strongest predictors of abalone age, and the random forest balance variance and bias well, while decision trees tended to overfit. In real-world applications, abalone age prediction can help fisheries optimize harvesting strategies. Models like XGBoost or Ensembles could further improve accuracy. Ongoing model monitoring is necessary to account for data drift. If deployed this strategy, this model can be used to monitor abalone populations non-invasively. Fisheries in Australia and New Zealand could integrate it into their harvesting practices to ensure abalones reach maturity before collection. By using automated image recognition with this model, age predictions can be made without manual measurement, improving efficiency in large-scale operations. And that's all for the assignment. Thank you.